All right. Okay. I hope you all practiced the R codes of lecture 7, and I told you to do it for do the sample test for different types of alternatives. For example, I did the two-sided ones, and I asked you to do for less than and greater than hypothesis as well. So you should have a question there if you did it properly. Did any one of you come across any problem once you tried this test? Anybody? Not the two-sided one, but the one-sided one. For any of these two, let's just consider this one, two sample t-test. No problem. Okay, so let me teach you that if you didn't notice, because that is very important. Okay, I wanted you to find it out yourselves, but if you didn't find, let me teach that to you. So from here, the hypothesis that we tested was mean age of breastfed infants is equal to mean age of non-breastfed infants, right? We had two categories splitted by yes and no status, the age variable, and we had two data sets. We compared the means, whether they're equal or not, and that is by the two-sided test, right? Imagine, so I'll take a new script for that because I'm going to upload it. Right. So here, let me just copy. Right. What if I wanted to test this one? You can type the word greater here, right? If you wanted to test this particular hypothesis, the alternative is greater. Sorry, alternative is less. No. This should be, this is it's not, so this should be this one, right? It's not should always go with the equal sign, right? So if it's not is this particular thing, right? What is h1? This one greater than this. I'll write it, otherwise you will not see what I really want to show you. So if this is h1, this is the complete opposite of this. It's going to be this way. So if this is the order, we give greater because this is the greater than sign. Which one is greater than what? Infants who are breastfed, mean age of infants who are breastfed is greater than non-breastfed, right? So that means this side is the greater part. So mean years, age years, this is given by age years, is greater than this side, age no. So if we want to test this hypothesis, this is the code that you have to run. Oh. I have to install, get the file. It was not here. Okay, it's installed, and I'll just run this code line. Now it's attached. Now we have to run everything. Just to make this code, this script complete, let me have all these. Where did I have this one as well? Just to make the script complete. Otherwise, you don't need this. And the attachment. Okay. So this is done, attachment is done, then these two. Now this. Now what's the problem? Okay, so when you run this thing, this is the p-value that you're getting, right? Okay, and here it is less than alpha, so we reject H naught. Now we can get the same p-value, right? So yeah, just forget about things. What if you interchange these two variables and keep this alternative as it is? What will happen? Let's check that one. Same hypothesis. What if you interchange these two? Here you, as the first argument you are giving age no, and as the second argument you are giving age yes. Can you see the p-value has changed? This is wrong. Why is it incorrect? Because when you give this type of a thing to R, it takes the first argument as the left hand side thing in your alternative hypothesis statement, and the second argument as the right hand side thing in your hypothesis statement. That is why you have gotten a wrong p-value. Yes, you are getting some p-value, but this p-value is not to test this hypothesis. So if an alternative way of checking this one is, if you interchange these two variables, the order that you give, you have to interchange this one as well, because interchanging these things means it's the inequality sign also interchanges, right? So if you want to obtain the correct p-value in a different way, that means by interchanging these arguments, you have to alter this one as well. So let's try that. Actually, I should copy this one. If you want to give the second argument first and first argument next, you have to change this one, because if you are giving the first argument to be age no, right? So age no is less than age yes, right? Age no is less than age, yes. That's why you have to change this word. Then you should be getting the same p-value. See, when you run this, you are getting the same p-value as above. So actually, to do this type of a hypothesis, this is method 1 and this is method 2. Right? Both these methods are correct. So why to confuse at the exam? Just put the leftmost statement, the variable which is relevant to the first leftmost statement first and the rightmost statement second, and then put the name of this sign as the alternative. So that is the easiest way of doing this. In case if you interchange these two, remember that it goes in left to right order. So if that is the case, this comes first. It's like interchanging this hypothesis statement. Same thing, this is method 1, right? Hypothesis is written to method 1, and alternatively, it's the same thing, right? It's the same thing. I'm just interchanging the sides without harming the inequality sign. Okay, it's just like switching these two. Same thing I'm writing. Okay, there's nothing different. Okay, so actually this hypothesis is tested in the first method. Where is that? Method 1, right? And this hypothesis is formed in method 2. But can you see these H1 and this H1, they are the same, right? There's nothing different in that. You all are math students, you all know this, right? 2 greater than 1, 1 less than 2, something like that. Okay, so this hypothesis, this second, according to the second method, this hypothesis statement means basically this one, and it is the same H1, right? So what I have to highlight here is just be careful when you are giving arguments, because if you didn't consider that and you consider only this sign to put here and you arbitrarily give names here, there can be a chance, there's a 50% chance of getting a wrong p-value. This is wrong. True that you are getting a p-value which is wrong, right? So just be conscious about that. Is that clear? Do I have to explain it once again? Is it clear?
Yes, madam.
Okay, thank you for confirming. So that one you have to practice and get to know. There's no rocket science. Just go in order. If I were you, what I do is I write H1 and go in the left to right order. I know the name of this inequality that is greater than. I know the name of this inequality that is less than. So depending on what I write here, I'm going to write the alternative. And depending on the left to right order, I'm going to give the arguments. If I were you, that's what I'm going to do, just to avoid confusion. It's not incorrect to do it in this way. In your R code, in the exam, I won't be checking word by word, right? Whether the alternative is greater, that is correct. No, I won't be doing like that. I am checking the entire line. If it gives the correct output, that's it. So there are several methods of writing things. So you don't have to worry about that because it's marked manually. Just be conscious about things. Okay, and also I think I forgot to mention, but in the R script I mentioned that in this one, usually when we go for a non-parametric test, we don't use the word mean. We in non-parametric statistics, you might have learned this in mathematical statistics 2 course. We usually go with the word median, and there's a reason for that. Why we go for a non-parametric test is because the data are not normally distributed. So that is the major thing that we are considering. We do the Shapiro test, the normality test, and if it is not normal, we go for the non-parametric test. The data are not normal means anyway it is skewed. It can be skewed. It's not always really. If it is distributed as T, it is again symmetric. But most probably data not normal means most probably it has a better chance of being skewed. When your data are skewed, is it meaningful to compute the mean as the measure of central tendency? It doesn't give the idea, right? If it is skewed, you usually, if you want to get a measure to obtain the central tendency, the tendency to go to the center value, you can go to mean, median, or mode, right? So in a skewed data set, it is more appropriate to go for the median rather than the mean, because in a symmetric distribution, basically mean, median, mode are going to be the same. Theoretically, they are the same, right? Practically, it should possess very close values, practically, right? When it is symmetric. So usually that is why in non-parametric tests, they are constructed for median. It is not wrong to use the word mean, but in case if the mean is not sensible enough, it is better to use another method of central tendency. The usual word that we use is median for non-parametric tests. So although you are asked to check whether the age is different from some value or something like that, you can reword that. It's not wrong to reword the hypothesis statement. I'm not crucially marking it, right? You have to have the word median here. I'm not checking on that because this is this computational statistics, but you all have gotten used to write some other method, other possible method of central tendency in non-parametric tests. That is the reason. It's not always the same. So what if this data are t-distributed? Still, you can use the word mean because it's a symmetric distribution, although it is not normal, right? So there are no hard and fast rules that you cannot use the word mean here. But you know, given that the data are highly asymmetric, you usually don't use the word mean because it's not representing the central measure, right? Just play around some data set, just take a couple of data with outliers to one extreme side, right, with outliers, and just manually compute or by using our compute mean, median, and mode, and see whether they are going very closer to each other or very different, right? So that is the reason. So at the exam, if you go for a non-parametric test, you can use any word. Just keep it in mind that mean is not always correct to use as a measure of central tendency, right? Keep that in head. It's okay to write either median or mean. That is fine. Okay, you can choose. Right. Any questions on that? Any unclear parts? Do I need to repeat it? Is that clear? Any problem with mean and median in forming the hypothesis? Quickly tell me.
It's clear, madam.
Thank you, Devani. Right. Okay. So today's new topic, again, we are going to discuss a couple of tests, which is very easy. So today my scope is to cover up the chi-square test for a single sample and Fisher's test and chi-square test for two variable case and the binomial sign test. Okay, they're not hard. Usually when we use chi-square test, when it comes to one sample test, you usually can form the hypothesis in terms of proportions, right? So let's go with an example. I think that will be very clear. Just write this down or take a screenshot, up to you. So let's say you are going to a bank and you have 4 different counters, right? This is the counter number. Let's say 1, 2, 3, and 4. Four different counters. And at the end of the day, people have kept records of number of customers served by each counter. So let's say 24 customers were served by the first counter for the day, for the entire day. 33 by here, 19 by here, and 22 by here, right? So it's like a survey on whether all the counters serve in the same speed, same frequency, or one counter is better than the others, or something like that. You can identify if it is different, you can by pairwise comparison or something like that, you can identify which counter is the fastest, right? So things like that. That is the practical use of it, general thing. Okay, so assume you want to check, let's say it's not, we usually construct the hypothesis in terms of proportions. So either verbally or by using notation, you can form the hypothesis. So let's say it's not proportions of the customers are equal. So it's not means null, no difference. So it's equal among all the customers, no difference. Equal for each counter, right? So our H1 is proportions of customers are not equal for each counter, right? So we are going to test this hypothesis. We have 4 categories, the counters, and we have the count data for each counter. So at this type of an instance, we go for the chi-square test. Actually, this is the one sample chi-square test because we just have a single sample, right? Assume assume that the customers are equally distributed among these counters, right? The probability that a customer would go for counter 1 is equal to the probability that a customer would go for counter 2. Just assume. So if that is the case, 1/4, 1/4, 1/4, 1/4. Probability is 1/4, 1/4, right? If there's equal probability for the customers to go, that means a customer can choose which counter to go at random without any other matter, right? Randomly they can choose between the counters. Assume that is the case. So assume the equal probability case for the moment, right? So there are express counters now. So sometimes in supermarkets also we can find if you have a lesser number of items, let's say number of items less than 4, there's a particular counter allocated for that. If that is the case, the probability is different, right? Let's say you have 3 counters and this is the express counter in the supermarket. Probability that a customer would go for this counter is different from the probabilities that the customers would go for these 2 counters if they are equivalent, right? These are normal counters. The probability that a customer buy less than 4 items is different from the probability that the customer buys more than 4 items, right? Those can be different. So in that case, we have to accommodate probabilities as well. But here, just assume customers can randomly choose between the counters, so the probability is equal. So if that is the case, we can perform chi-square test, and it is very easy. It's just a matter of giving the customer data in a vector and just calling the chi-square test. It's very easy, right? So the code for this is, you can take a screenshot of this because I'm going to discuss a couple of things here after. Take a screenshot. Or just quickly write it. Okay. Okay. If this is a different topic. Okay. So let's say customers, right? You are going to give the values in a vector. So the numbers were 24 customers in the first counter, 33, 19, and 22, just the random values for each counter. We run that. And we have to perform the chi-square test. So this is the command to perform the chi-square test. This one. Okay, so we just have a single sample, so it's just a matter of giving the customer vector as our data set. When we run that, chi-square test for given probabilities. So here we assume the probabilities are equal, so we don't have to give any probability. If we didn't give any probability, they take it as equal probabilities by default, right? So this is the data, and this is the chi-square value. Actually, this is the value of test statistic if we compare it with some critical value, degrees of freedom, and this is the p-value. So as long as they give the p-value, nothing to worry about checking the statistical tables or whatever it is, just take the p-value. So here also you have to write the hypothesis just like I did in the whiteboard. So here the p-value is this. You have to write the decision rule, decision, and conclusion in plain language. So that of course you all know, right? So I won't be repeating it in today's lecture. If you have any questions, please ask. Okay, so the decision rule is reject H naught if p-value is less than whatever the significance level. So let's say 5%, if p-value is less than 0.05. At the given significance value, you have to check. Okay, so for the woman, let's say it's 0.05, and this is actually greater than that, which means we accept H naught. We do not reject H naught with 5% level of significance, right? So what is H naught? H naught is the proportions of the customers are equal for each counter. So there's no difference, it's equal, right? According to the data, the proportion of each customer going for reaching the counters is equal for every counter. There's no difference between the 4 counters in the bank. So something like that you can say as the conclusion, right? Second case is assume that you have unequal probabilities, right? second case. Right, let's say for the first counter it's 0.25. It should be a value between 0 and 1. 0 point, let's say 3, let's say here 0 0.2, 0 0.22, something like that. Okay, just see, add up and see, these should add up to 1. It must be, otherwise this is not complete. Why? The probability of sample space should be equal to 1. That is probability theory. So these should add up to 1. Let's see, 5, 3, 8, 2, 10, 2 and 1, 3, 5, 5, 10. Okay, 1.0. So these are the probabilities that we give. So if this is the case, if these counters have different prior I don't want to use that word prior. If these counters have different probabilities of a customer to come, and for the day, if these are the number of customers that these counters occupied, let's do the chi-square test to check this hypothesis. Same hypothesis when the probabilities are different, right? Proportions of the customers are equal for each counter. So although the probability values are given according to the data set, the population value can be changed or might not be changed, because these, by looking at these probabilities, we can see that they are slightly going in line, right? But we really cannot say by looking at the data. We expect, if this is happening, we expect these probabilities to be 0.25, 0.25, 0.25, and 0.25. We expect that, right? But in real terms, it's not the case, but we check that, okay, using a hypothesis. So if the probabilities are known, it's just a matter of giving the probabilities. So for this one, this is the data. And how do you give the probabilities? P equals, as a vector, you have to give the probability. So even if you have another pre-specified vector like probabilities and you give the probabilities here, you can just call it by the name, right? That's fine. Different way of giving the arguments. So I give the probabilities in order. I have to give it in order. I can't switch, because this probability is for this counter, right? The next probability is for the next counter, likewise. 0.2 and 0.22. So if we do the chi-square test for this, it passes a different key value. Still, it's the same. Even by looking at this, we can see that these probabilities are very closer to each other. We cannot exactly say, but seemingly it is close to each other, which means the probability that a customer would choose a counter is equal, or they can choose at random. There's no counter serving at a faster pace than the others. So you can interpret like that. Just simply you can say proportions of the customers are equal for each counter, something like that. Okay, I hope that is understood. This is chi-square test for a single sample, one variable or one sample chi-square test. And also chi-square test can be used to test the association between two categorical variables when we have count data. Of course, if when we have a contingency table or two-way tables, we can perform chi-square test to check the association between the considered categorical variables. So that is the two-sample case. So let's discuss another example. Right. If I'm going too fast, just let me know. If you want more time to write down things or think about things, please interrupt me and just ask for some time. Okay. I'm doing this in my pace, so it's up to you to tell me that if there's any problem. Okay. Next example. Let's say it is interested to determine whether there's any association between absenteeism and gender, right? So you have males and females in the column category as the column category, and present absenteeism as the row category. Okay, so these are the two categories in absenteeism, and these are the two categories of gender. Let's say you have 51 people who are males and who are present for something, and 43 females who were present, 21 males who were absent, and 4 females who were absent. Right, this is a two-way table, two variables, so two-way table with two categories each. Each variable has two categories. It doesn't have to be two all the time. It can be even many, right? So your H naught is what? There is no association between gender and absenteeism. So H1 is there is an association between gender and absenteeism. You have to write it completely, right? So for this, we want to perform either chi-square test or Fisher's test, right? So just go through your mathematical statistics notes, mathematical statistics 2 notes, and see when you are using the Fisher's test, when you are using the chi-square test, right? Usually, I'll tell you, but you can go through your notes, right? These are the observed frequencies. You compute the expected frequencies. How do you compute that? Take the total here, take the total, take the row totals, and take the grand total, right? For this one, what is the expected frequency? This total times this total divided by the grand total. For this one, what is the expected frequency? This total times this total divided by this grand total. Okay, so likewise. You compute the expected frequencies, and if 80% of the data, if at least 80% of the counts are greater than 5, you can use chi-square test, right? So you have 4 cells here. 80% means what? 4 times 80 divided by 100. So approximately around 3 cells, 75%, right? So you can perform chi-square test if at least 80% of the cells have expected frequencies as 5 or greater. Otherwise, you cannot use chi-square test. You have to go for the Fisher's test, right? So that is the deciding factor. Just go through the notes, right? But anyway, without looking at anything, just to tell you out how to give the code and all that, that is the scope of this. That is deciding on the test is your prior knowledge, prerequisites, right? I'll For the same example, I'll do the chi-square and Fisher's test both, right? It might give the same result, sometimes it might not, right? So you have to decide which test you are going to use based on the test assumptions. So I'm not talking about that. I did talk, but I'm not checking it that at this moment. Just to teach you the code lines, I'm doing both the tests, right? At the exam, you have to compute and see which test to be used. Okay, if this is the case, if we want to test the hypothesis, we can go for two sample chi-square or the Fisher's test depending on the assumptions. So let's see how we are going to do that. First, we have to take all the data in a matrix. Why? Because this has rows and columns. This can't be given in a vector just like in the first case. First case was a one sample case. You can use a vector. Here it is two samples, right? You have to go in a 2 by 2 matrix, right? And it should, the matrix should look like this. Basically, you can't interchange things, right? If you interchange, you have to be careful with the final conclusion. You can interchange this one and this one, or this one and this one, but you can't interchange all these, right? So be careful with that. Just follow the order. So you have to store it in a matrix, just like what you did in the previous case, just like how you stored it in a vector. So let's say table T, right? Matrix, right? So I'm going to give out the values in order. So 51, 43, 21, and 4. So I gave it in the row wise order, right? So my first row, the values from left to right is right are 51 and 43. In the bottom, I had 21 and 4. So I'm giving it row wise. So if that is the case, I have to say by row equals true. I'm giving it row wise. Right? If you are interchanging, you have to deal with this variable, this argument. Okay. Anyway, the matrix should look like the data set. That's the requirement. And you usually give the number of rows. That's enough, because if you give the number of rows, they know the number of columns because they know the length of the data. Right? We give this. Let's print it and see whether we are getting the same pattern, just to make sure. 51, 43, 21, 4. 51, 43, 21, 4. What if we interchange? If we say false, or if we say by call, that is by column wise, by call equals true or something like that, we are getting a different order. See? Different, right? So be careful when you're giving the matrix. Just follow the order of the question. Okay, so I recompiled it to update our matrix. So this is the correct matrix now. Those are the things that you should be careful, right? Okay, so you can perform the chi-square test. Chi-square test, and it's just a matter of giving the matrix there. This is the p-value. If you want to get the Fisher's test, There's nothing called two sample Fisher's test. Anyway, the Fisher's test is designed for two sample case. You can use the same thing, only it's very easy. It's just a matter of giving this command, Fisher dot test, and you give the matrix. Here you are getting a different p-value. Just refer to the p-value, it's enough. Can you see there's a slight difference in p-values? Because why? This is a 2 by 2 case, right? Each variable has two cases. So 80% is like 3 out of 4 is 75%. So if they have to accommodate 80%, then they have to consider all the cell values. But you notice single cell value was less than 4. I don't know whether the expected frequency is going to be less than 4. That we have to compute and see. 44 times, 47 times 25 divided by the summation of these. We have to compute the expected frequency here and see, right? Maybe expected frequency is greater than 5. I don't know. I didn't compute. That is why they give the same decision. It's different p-values because two different tests, but same decision could be made. H0 is rejected, right? Less than 0.05. It's not rejected because either you use this test or this test. It doesn't matter for this case, for our case, right? So just be mindful about the expected frequencies and whether it meets all the assumptions before putting any test. If the question paper doesn't tell you anything about it, if the question paper says put chi-square test, just without checking anything, just put that. It's okay. Put a suitable test to check the association, then you have to check for model assumption, the test assumptions, right? Just check this. It's easy to compute and choose between the test. Here, same decision. So when you are asked to do the test, just don't write only the p-value. Make your decision based on this p-value. Write all H0, H1 decision, rule, decision, and conclusion in plain language. That is how you should perform a test. Right, so that's all about chi-square and Fisher association tests. There's one test you left for today, that is binomial test. I'll do a small recap for you. I know you all cannot remember. I know that. So let me introduce the binomial test, the non-parametric technique that we used. You have done this. You have done the exact thing last year, but let me introduce that to you. This is out of my scope, but I'm doing it. I feel that you will need it. Okay. Can I move forward? Is everything clear to you? Do you need any time to write things down or anything? Ask questions? Okay, I suppose no. If there's anything, just let me know. Right. For the binomial test, actually, I gave you a small activity sheet. I don't know whether you noticed it. Okay. It is there in your LMS under material. I just put a drive link for this one. Okay, binomial test examples. I'm not very sure whether you did the same set of examples in your mathematical statistics 2 course. If so, you should have already gotten the p-values for these, but let's do it once again just to recap. Okay, concentrate on this particular question. First one. test the following hypothesis using the given sample information, right? It says pi is less than or equal to 0.5 versus pi greater than 0.5. So this is a one-sided case. Alternative is greater than, right? One-sided test, alternative is greater, right? Is the proportion of males in the proportion. So let the sample size n be 10 and x be 8. X is the number of successes in the sample. So it could be the proportion of males. So let's say males and females, right? So number of males in this sample is 8. That is what it meant by number of successes. It really depends on how you define the random variable here, right? So here the parameter is the proportion of males. Random variables is what? Number of males in the sample. It's the random variable, right? So the proportion is our interest. This is the sample size, and this is successes means what? Number of interest. So we are interested about the male proportion, males in the population, not the females. So count of males. That means 2 females, 8 males. Just perform this hypothesis. We are going to check whether the proportion of males is less than 50%, less than or equal to 50%. That is what we check. Okay. According to this, we can say C it is greater, right? Researchers claim is what? Proportion is greater than 0.5. So all these are meaningful, right? By looking at the sample, we can see 2 to 8, that is the ratio. 2 to 8, females to males ratio. But for the population, we are doing the hypothesis. This is the sample. So basically, this is an example discussed on the binomial test because we have 2 outcomes, successes and failures. In our case, females and males and females. Failures are females, successes are males, according to our question, right? So this is the number of successes. In other words, this is the sample size. So it's just a matter of performing the binomial test. So I'll just do some manual method. If you are asked to do it without software, how you would do, right? So we can say x naught is binomially distributed with number of trials 10, that is the sample size, and 0.5. Right? This is the hypothesized value. Okay. Here, how do we compute the p-value? So actually we have to give the domain of x. X can be, x means what? Number of males. That is our random variable. Why? Because 5 is the proportion of males. You can either call x as the number of females and just do it in the other way around. Still you should get the same thing, but it's confusing. So domain of x is number of males can be 0, it can be 1, up to 10. Can number of males be 11 if the sample size or the number of trials is 10? No, right? It should end here. But in binomial distribution, domain is written from 0 to n. N is the number of trials. So this is the case. How do we do this hypothesis? So I'll just write h naught once again here. You have to write let phi be the population proportion of males, right? So let's notice this is what we want to check. So how do we do the p-value? Is equal to probability that number of x, this is our sample, greater than, we always have to put this one, right? This is the sample, number of males in the sample. So this is what we check from the probability, right? So if this is the distribution, it is not continuous, right? We are checking whether the proportion is greater than some value. So this is x. We are checking whether it's greater than 8 or equal to 8. Right? This hypothesis test is designed to do like this. Okay. I'll tell you about a shorthand system also in deciding this sign. But before that, just try to understand, right? We are going with the more extreme case. So that is, just go with the alternative if this is not understandable. So it is the greater than sign. Here also greater than sign. That is what we check. Okay. It's easy. It's not confusing to go in this way. So how do we compute this? Known that the x is binomially distributed. If we do this manually, x grows from, so we are checking whether the male proportion is greater. 8 to 10, 10cx times 0.5 to the power, this is x, times 1 minus 0.5 is what? Again 0.5 to the power 10 minus x. When you input this into your calculator, you are getting this value. Something like this. Okay, so based on this one, right? 0.05. So our decision rule is what? Reject H naught if our p value is greater than this value. This is alpha. This is one-sided, so we take alpha, right? Reject H naught if p value is greater than this, sorry, less than this value. It should be less because p value is again area under the curve. So if this particular value is greater than this critical value, that means the area under the curve is less than alpha, right? This is very easy. It's understandable. Simply write decision rule. Reject H naught if p value is less than alpha, right? So what is the decision here? Actually, it is greater than 0.05. So we do not have enough evidence to reject H naught. I'll write it in short. Do not reject H naught with 5% level of significance. Conclusion is what? This is correct. That means, sorry. Reject H naught if p value is less than alpha. Ours is greater. So we do not reject H naught. That means proportion of male population is not greater than 0.5. Although the sample says the proportion, this simple P stands for sample proportion, right? Sample proportion is what? 8/10, right? We have 10 members and 8 males. So sample proportion is 0.8. Although this sample value is greater than 0.5, this is for the sample, right? What if we take another sample? It is different. It doesn't have to be 0.8 in all the samples, but based on the data, when we do a hypothesis test for the population parameter, that is the population proportion, irrespective of this, it says that H1 is correct. So you can say proportion of male population is not greater than 0.5. That is your conclusion. Proportion of male population is, you can either say less than or equal to 0.5, or you can say not greater than 0.5, or you can say not greater than 50%. Right? If you are saying less than, less than the proportion of male proportion is less than 0.5. If somebody write like that, it's wrong because it's less than or equal, right? So don't forget about this if you are writing in terms of H0. So I advise my students to go with H1 because it's very straightforward. It's up to you, doesn't matter. If you write proportion of male proportion is less than or equal to 0.5, that is acceptable. It's correct. But if you write proportion of male proportion is male population is less than 0.5, I cannot mark it correct because it should be less than or equal. It's better to go with this. So this is how you do this manually. You have done this. I don't know whether you did the same example last year, but you have done this. You have learned this. So our intention here by using R is to avoid this particular part in calculating this p-value. It's just a matter of giving the arguments correctly to perform the binomial test, and it gives you out the p-value. All what you have to know is write the hypothesis, put the decision rule, make the correct decision based on the p-value, and write the conclusion. But I think these things are not very challenging to you all by now, but you have to be cautious when you are giving the values for the arguments in R, right? So you have to decide what is the number of successes, right? So in R, how you do it? How do you do it? So binomial test. Example 1. Okay. Here. Yes, you can either use the help here. So actually it is binom dot test, right? Here these are the argument x, n, this one, and all that. Just to let you know about things, you always don't have to use the R help itself. The same documentation is available in the web as well. When you type binom this one, you're getting something like this, R documentation. It's the same thing. Most probably it is the same thing that you get here when you get help. Binom, I think it should be the same. Did I type it in the correct place? Yes, I'm getting this thing now. You don't have to stick to R only. Same thing is given here. Sometimes with an example, with a compilable example, right? So here, what are the arguments? X means number of successes. Number of successes. So that is quite straightforward. It depends on how you define the random variable. So here in the question, it says number of successes is 8. But there are so many methods. I'll teach you the other method in the next example. N is the number of trials, right? And the rest P is hypothesized probability of success. So this is the hypothesized value. Binom n comma theta. So that theta value is this. Alternative, it's the same way as earlier. Confidence intervals if you want to have. So these are the arguments. Usually we make use of these things, right? So for our example, X is what? Number of successes is what? 8, because we have 8 males in our sample, which we are interested about. N is what? Number of trials is 10. What is our P? If I go to this is our N, this is our X, and this hypothesized value is our P, right? And this is a greater than type test. Okay, so you have to say alternative within double quotes greater. Here we are getting the P value as this. Is it the same with the one that we calculated? Yes, right, 0.0549. So they are giving it to the 5th decimal place. It's what we computed. 69 is rounded off to the 4th decimal place, so that's fine. We are getting the same p value, right? So all these computations could be done by using R. If you can clearly define what is the number of successes, what is the number of trials, and the hypothesized value, and the direction, of course, the alternative hypothesis, whether it is greater or less. So this is greater, right? This is greater. Go with the alternative is greater. So as long as you can compute all this, you're getting the p-value. It's very easy, right? So that is the answer for this one. And if you say test, it's not enough to give the p-value only. You have to write all the things, all the conventional things in a hypothesis test. So I'm repeating this because it's very important. Okay. Any questions? Can we move on to the second one? Okay, no questions. So let us see. Second one, an experiment is continued to determine whether a coin is biased, right? So what is the hypothesis? It's not is what? There's no difference. No, coin is unbiased. It's one is what? Coin is biased. That means probability of getting a head is 0.5, or you can say probability of getting a tail is 0.5. Both the ways you can define it's not, right? But unbiased means the probability of getting a head is equal to probability of getting a tail, and that's 0.5 each. So this question, actually this question itself says the coin is flipped 10 times, so this is the number of trials, right? We have 10 observations, 10 is the sample size, resulting 8 heads and 2 tails. So here in these questions, they have given you 8 heads is a success and getting a tail is a failure, right? So that is just one method. Okay, they have specifically told you, but even you can interchange these things by changing how you define the random variable and still get the same answer. Both are correct, right? Do the results indicate that the coin is biased? So two methods, same thing. It's just the difference is just about defining the random variable. According to this question and how they have told us, their random variable is what? event that we get a head, number of heads that we get in a coin toss, right? That why this is a success as they have stood. But if you are not given these two, you can decide, right? Getting ahead is not the success all the time. What if you define the random variable as number of tails that we get in a coin toss, right? In coin tosses, in a number of coin tosses. So we'll do the both methods, and I'll show you that depending on how you write the random variable, how you form the random variable, you have to make small changes, but still you should be getting the same answer, right? Method 1. We'll just go in the method that they have told us, right? Let x be the number of heads. So that is the success. Okay, if that is the case, x is binomially distributed. We have 10 coin tosses and we are checking whether the coin is biased or not. So what is the success probability? If it is unbiased, we should get a 50% chance of getting ahead, right? So this is a, without giving it directly, they have said it in just simple language. So we have to decide that this is 0.5. Okay. And how do we get the p-value? So in this thing, they say this in the sample, they have gotten 8 heads and 2 tails, altogether 10, right? So how do we compute the p-value? Before that, what is our H0 and H1? Yes, coin is unbiased, coin is biased, but if we write in mathematical terms, let pi be the proportion of heads, right? So here, if it is unbiased, this should be the proportion. If it is biased, it cannot be. So this is a two-sided test. Can you see it is a two-sided test? Right? So if we are dealing with the number of heads, out of 8 and 2, what is the more extreme value? This one. Why do I say that? Just look at this carefully. Let's say this is the count axis and this is the proportion axis. I'm just making this very much clear to you all, right? As much as possible. So if the coin is unbiased and if we have 10 in total, 10 coin flips, we have to get 5, right? 5 heads and 5 tails if it is unbiased. But we have gotten 8 heads and only 2 tails. So 8 means 8 is in the right hand side of this. So we are dealing with this. In other words, if we take the proportion axis, this is 0.5, this is 0.8, the sample proportions, okay? This is 0.2. So if we are dealing with heads, it is to the right side of your axis, right? So this is a two-sided case now. We have to just pick one side to decide on the p-value. So how are we going to decide that one side? In the distribution, if we have the distribution, just because this is to the right side, we darken this side. Just to test this. In theory, if we have a two-sided test, what are we going to do? If we don't know whether this is symmetric or not, we are going to read this value, we are going to read this value. If our computed test statistic falls in one of these regions, we are rejecting it's not. Right? This is alpha over 2 and this is alpha over 2. That is what we do. Right? Here, we are taking it to this extreme and check that. So here we have more number of heads and that is our random variable. So in this particular case, we check our hypothesis to the left end with this. We compare our p-value with this, not 0.05. We compare our p-value with alpha over 2. Because this is a two-sided test, we are checking with only just one side. And we have to be selective, which side, left end or the right end are we using. How do we select that? We go back to the random variable and identify the success. We go to the number of successes, and in this proportion line, we check to which side that falls to. So we have more here, so it falls to the right side and we are checking it in the right end. It's easy to remember it like this, right? So how do you compute the p-value? Probability x greater than or equal to this value. That is how we decided on this inequality sign, right? So if the p-value is less than alpha over 2, we reject h naught. Be careful in writing the decision rule, right? So decision rule is what? It's the same p-value as earlier, right? Just because of the same values that we're dealing with. Decision rule is what? Reject h naught if p-value is less than, please remember this. To the two-sided case, you write this, right? To one-sided case, you write alpha. So here also, when you compute the p-value with 0.057, same thing because it's the same value. So our conclusion is that coin is not biased. We do not have enough evidence to reject it's not because this is greater than 0.025. Right, this value is. We are comparing this value with this value, not 0.05, right? And our decision is what? We do not have enough evidence to reject it's not with 5% level of significance. The significance level doesn't change, right? Significance level is alpha. When you're making the decision rule, you have to involve alpha over 2. That's it. You can't say we do not have enough evidence to reject it's not with 0.25% of 2.5% of significance level. You can't say that. That is wrong. Significance level is 5%, alpha percent, right? It's alpha, not alpha percent, 100 times alpha percent, right? Significance level is alpha. When you're forming the decision rule, you have to consider alpha over 2 just because it is two-sided. I hope that is clear. These things should not be taught in this course actually. It should be taught in the Mathematical Statistics 2 course. But I know you all have forgotten. Just to give you some recap, I did this. So just be mindful on this when you're making the decision. So in this case, here, what you have to do is, how do you give the hypothesis? First method. This is the same, this is the same. This is the same hypothesized value whether the coin is biased or unbiased. So it's 0.5. Alternative is greater. Wait. Yes. Alternative. If you give two-sided, let's see. If this is the case, yes, you're getting this p-value. It's the same p-value that you construct. Right. And second method, you have to give the alternative like this. And in the second method, let's say x. Let's say x is the number of tails. That is your probability of success, the random variable. So let's say y for the moment. To avoid confusions, I write y. Number of tails. So this is the second method. Example 2, method 2. Here, y is binomially distributed, 10 and 0.5. Here you don't write 0.2 or 0.8 or anything. This is the hypothesized value, right? Here, how do you compute the p-value? Why? Because successes, number of tails, how many heads you have? 8. How many tails you have? 2. Just draw this count axis and the proportion axis, right? If it is unbiased, it should be 5. It is unbiased, the proportion should be 0.5, right? We have 8 heads, 2 tails. So the proportion is 0.2. That means 2 divided by 10, right? This is 0.8. Here we are dealing with this one. So this proportion, right, it is to the left end. So in theory, we discussed about alpha over 2 here, alpha over 2 here. So we have to decide on which side that we have to deal with in this sort of a representation. So whatever the distribution it is, it's the left end. Still we are dealing with areas, so the decision rule remains the same. When x is equal to 2. If our computed p-value falls here in this region, we reject h0, right? So the decision rule is reject h0 if p-value that we computed here is less than. Please remember this again, because it's like this, we are forming a two-sided test to a one-sided test in order to get the results, right? When you compute this manually, you have to get the same thing. Just you know how to compute this, right? I'll just do it here. Summation x goes from 0 to 2, right? 10, sorry, y, actually y here. 10 cy, 0.5 to the power y, 1 minus 0.5, that is 0.5 to the power 10 minus y. So when you compute this, you are getting this one. This is how you write. When you write it in manually, this is how you write. Okay. So it is to the lesser end. 0 to 2. Why? It's less than or equal to 2. 0 to 2. Here the domain is y equals 0, 1. Y can be anything. Number of tails can be 0 to 10. It can't be 11, 12, anything. It has to be 0 to 2. So probability that the random variable is less than or equal to 2 means what? It can be 0 plus 1 plus 2. Okay, that is why summation 0 to 2. This is how we manually do. Okay, anyway, whichever the direction we consider, we have to come up with the same answer because the decision should be the same. right? It can't depend on the random variable. How you define the random variable? So this is the second method. Here we transform our two-sided case to a single side. And now our x is what? In method 2, x is 2. Number of successes, number of tails that we got in this coin toss, right? This remains the same. Trials are the same. This is the same because we are checking whether it's unbiased or not. Alternative is less. Why? We transformed our two-sided one to less than type. Same p-value. So the same decision. So you can use either of these two methods if it is a two-sided case. It depends on how you define the random variable. Is that clear? Any confusions, questions?
Yes, ma'am.
Oh, great. Thank you. So I think hopefully you can remember this. That's better if you could remember. So shall I proceed with the third example, and that's going to be the last one today? And or you want to write this down or think about it? Just tell me if you want more time. I'll just give you a little time. Okay, you might be wondering whether you can't put two-sided for this, right? There's no difference. If you that is actually wrong. You cannot get the correct p-value. You might be thinking this is a two-sided case. Why can't you put two dot-sided here? Just because the way that you give the arguments, you really cannot, because you have to specify x is this. If we say x is this and two-sided, it's going to be some p-value for like this, right? If you say x is this and two-sided, then the same p-value, 0.1094. 0.1094. It's not the p-value that we should get, that we are supposed to get, right? Decision remains the same, but p-value is wrong. So if you use binomial test for this purpose, it's the same way that you do your calculation manually. You have to transform it from a two-sided case to a single-sided case and do it, because there's no way of getting the correct p-value when we give, because it does not depend on the number of successes actually. Either it is this or this, it gives the same p-value. It doesn't make sense. So think about this, and if it is a two-sided case, try to get the correct p-value by doing one of these. Okay. This third one and the last one for today. Let phi be the proportion of defective items in the sample. In a sample of size 10, there were only 2 defective items. The other 8 are non-defects. Okay. Is it reasonable to conclude that the proportion of defects is less than or equal to this? So actually, what is the hypothesis here? The equality sign is there, so this is the H naught. and h1 should be the greater side. Okay, let's just manage it. Example 3. So it says pi is the proportion of defects. So our successes is what? Successes is defects, number of defects. Failure is non-defects. Okay. And in the question it says we have of size 10, 2 defects. We have 2 defects. So if it is size 10, we have 8 non-defects. H0 is what? Pi is less than or equal to 0.2 versus H1 pi is greater than 0.2. So let x be, since our successes is number of defects, we are going to define our random variable as number of defective items, number of defects in short. So we know that x is binomially distributed with 10 trials, and this is the success probability. Don't put 0.5 here, it's 0.2, right? And how do we compute the p-value? So here, it's the same way. Count axis and the proportion axis, right? 10, and now this is our hypothesized value, 0.2. Right. So here, this is our alternative number of defects is 2, right? We are checking whether the proportion of defects, so this is the proportion of defects is 0.2. We are checking whether it is greater than 0.2. This is our alternative, right? We are checking whether the proportion of defects is greater than 0.2. So we have 2 reasons. Simply, we are checking whether the count of defects are greater than 2. In other words, if this is defined using counts, so this should be 2. If this is usually for parameters, we usually go with means, proportions, medians. It's not wrong to go with the count, but usually we go with the proportions. So if we are dealing with proportions, we are checking the same thing, proportion of defects, whether it is greater than 0.2. So actually, when you do the distribution, this side, so this is the left side, this is the right side. They have colored the right side, so we are checking to the right end. Actually, you don't have to do this. The shorthand method is what? Look at this sign. If it is greater, go to the right side. Look at this sign. If it is not, go to the left side. Right? Yeah. So that is very not nice to say like that. This is the idea why we go in the alternative side. This is the meaning of forming the decision rule. Actually, you never go wrong if you understand this. Okay. So what is the p-value? How do you compute the p-value? Probability x, we are going to the greater side, right? Greater than or equal to. X is the count, right? X is the count, so we have to deal with the count. Now don't confuse, it's not the probability x greater than or equal to 0.2. Always get the meaning. X is the count. See what is x? X be the number of defects. It's a count. Our hypothesis is formed in this way. Don't confuse. We are checking the p-value in this. So why we don't know to write the p-value using this? We know the distribution of x. We don't know the distribution of proportions. We know the distribution of x. So when we are writing the probability statement, we write it in terms of what we know. As long as you know the distribution of this, you know how to write the probability statement. So what is x? X can take values from 0 to 10. Maximum value that x can take is 10. So this is basically the summation. X goes from greater than 2 means 2, 3, 4, 5, 6, 7, 8, 9, 10. 2 to 10. I want you all to write this and get the answer. Don't use R. In the chat room, it's difficult to type this. Just get the final answer here. You can use your scientific calculator to do this. Right? You don't have to add term by term. The summation mark is there in your calculator. I'll give you time. Just if I wrote this, it's just a matter of copying it to the calculator. So I won't do it. Get the answer and put it in the chat room. This is the probability statement. This is the distribution. I want the answer of this. Just give me the answer. I'll give you 2 minutes for this. I'm glad that one person could come up with the answer and the answer is correct. Thank you for responding. Others? The person who just answered me, the answer is correct. It's okay to go wrong. I'll tease you. Sometimes you might have forgotten the PMF of binomial. Okay, another person answered, and that is 1, 2, 3. That is correct. I think the problem is with the decimal places. So up to the 1, 2, 3, 4. Up to the 4th decimal place, it's correct. Even the previous person's answer up to the 4th decimal place, it's correct. Yes. So yeah, maybe for some accuracy issues. Right. Thank you for responding. So I think this is easy. Both your answers are correct. We'll see how we got different 5th decimal places. We'll see. If the statement is this, anyway, your answer should be correct. Am I recording this? Yes. So what is the PMF, probability mass function of binomial 10 CX? Right? See whether you have gotten the correct statement. Sometimes there could be minor issues with similarities with the final answer, but issues with the statement. So actually I got my answer for the 4th decimal place. So I don't know which of yours answer is correct, or maybe both of you are correct. But we'll see. If you have written this probability statement, then that is the correct thing. What is the probability of success? 0.2. Did anyone write 0.5 there? No, right? 0.2 to the power x times 1 minus 0.2 is what? 0.8 to the power 10 minus x. If this is the statement, your answer is correct. So what I got as the answer was 0.6242. I didn't compute it to the next decimal places. Anyway, we'll see. We'll run the R code and see what it gives. Very good. So yes. Right. Here, X is the number of defects. So we have 2 defects here. That is the success. So it is 2. Number of trials that we have is 10, right? Hypothesized value is 0.2, right? We have the H0 and H1 formed with 0.2. Alternative is the side of the alternative hypothesis. So our H1 was pi greater than 0.2. So this should be greater. This is the p-value that it is. Any questions? The ones who couldn't come up with answers, is that clear to you now? Still, are you finding it difficult, or do you have any complications? Let me know. This is the last thing that we are going to discuss for today. And people who came up with answers, was that the probability statement that you wrote? Just check it once again, because you have gotten the 5th, 6th decimal places. Just double check whether you got this statement. If that is the case, you are correct. If you have any questions, please ask. So based on this p-value, this is very much greater than 0.05. So our decision rule is what? Reject H0 if p-value is greater, p-value is less than alpha. Here it's not alpha over 2. This is one-sided, right? One-sided. So reject H0 if p-value is greater than alpha. Actually, the H0 can be rejected because if p is greater than alpha. So the conclusion is what? Proportion of defects is not more than 0.2. Proportion of defects is not more than 0.2. I'll simply write it here, the conclusion. According to this, H0 is accepted because it is greater than 0.0. So this is correct. You can either write proportion of defects is less than or equal to 0.2. When you're writing, you have to write it in words. You can't write proportion of defects less than. You can't write things like this for the conclusion. If you're writing this, you have to write it in language. Proportion of defects is less than or equal to 0.2. Likewise, you have to write It's easier to write it in terms of this. Proportion of defects is not more than 0.2. It's easy. However it is, you have to keep it in plain language. Is this clear?
Yes, madam.
Okay, thank you very much. And thank you for participating today's lecture. As long as you don't have any question, if you don't have any questions, you can leave the meeting. Thank you and stay safe. If you have questions, please stay and ask.